Am I on? Yeah. So yesterday I told you about holonomy groups of connections, first on vector bundles, and then the holonomy group of a Riemannian manifold, meaning the holonomy group of its Levi-Civita connection. Like just to start with one observation about holonomy groups of products. So if we let x and g and y and h be Riemannian manifolds, so then we can take the product manifold x cross y, whose dimension is dimension of x plus dimension of y, and the tangent spaces of x cross y are just direct sums of tangent spaces of big X at a point little x, direct sum with tangent space of big Y at a point little y. And we can also take the, well, it's written as I write it as a product G cross H, but really it's a sum. So the product metric is if you have T at x comma y to big X cross y is equal to, or at least isomorphic to, Tx of x direct sum Ty of y, big Y, then G cross H at the point little x y is G at x direct sum H at y. So this is really just a matrix G, X, H, Y, and then the off-diagonal times are 0. So we can define product metrics like this. And so then it's pretty easy to work out that the holonomy group of the product metric G cross H is the holonomy group of G cross the holonomy group of H. So to see that, if you took a base point x0, y0 in x cross y, and then you took a loop in x cross y, that's just the same thing as a pair of loops, one loop in x and one loop in y, but traversed at the same time. And then if you think about the parallel transport around that loop, you'll see that somehow the loop in x, the parallel transport around that gives you the automorphism of Tx0 of x. The loop in y gives you the parallel transport about Ty0 of y. And so you just act by an element of the holonomy group of G acting on the tangent space to x0 at x, and an element of the holonomy group of H acting on the tangent space to y0 at y. So holonomy groups of products are just products of holonomy groups. So in particular, note that the representation of the holonomy group of G cross H on, well, it's really R to the dimension of x plus dimension of y, which we can think of as a direct sum, R to the dim x, direct sum R to the dim y, is reducible. So we should always think about a holonomy group not just as an abstract Lie group, but as a Lie group with a representation on R to the n. So a holonomy group is a subgroup of GLNR, or O of n. And in this case, the representation is the sum of a representation on R to the dim x and a representation on R to the dim y. So if x and y have positive dimension, it's a reducible representation. So that's going to be important later. Okay, so next let's have section 2.3 on holonomy groups and curvature. So we're going to see that there is a deep relationship between the holonomy group of a Riemannian metric and the curvature tensor, Riemann curvature of that metric. Basically, if the holonomy group is special, if it's a proper subgroup of SON, then that's going to induce linear restrictions on the curvature, force the curvature to live in a smaller vector subspace of the possible subspace of curvature tensors, and that has a lot of useful consequences. So let's state a theorem. Theorem 2.1. Let's take X, comma G, be a Riemannian manifold. And let's pick some base point little x0 in big X, which is the base point we use to define the holonomy group of G. So then the holonomy group of G sits inside the automorphism group of the tangent space to x0 at X. This is a Lie group, a Lie subgroup, so it has a Lie algebra. Which I'll write as a curly hole of G. And this is a vector subspace, in fact a Lie subalgebra of the Lie algebra of the group of automorphisms, which is just the endomorphisms of Tx0 at X. By this I just mean Tx0 at X tensored with T star x0 at X. But you can think about this as a Lie algebra or even an algebra because you can compose things there. Okay. Okay, so then the conclusion is that the Riemann curvature R of G has R at the point x0 lies in the Lie algebra whole of G tensored with the two forms lambda 2 E star at x0 of X, which is contained in end of T 0 at X tensored with the two forms. Okay, so well, we knew already that the curvature lies here. The conclusion is that it actually lies in this vector subspace, so the endomorphism part of the curvature has to lie in the holonomy Lie algebra. Okay, so that's just at that single point. In fact, this is true in some sense at every point. To make this precise, let's say more generally, if gamma going from 0, 1 into X is a piecewise smooth path from x0, which is gamma of 0, to x1, which is gamma of 1. So that the parallel transport map P gamma takes the tangent space at x0 to big X to the tangent space at x1 to big X. That's an isomorphism. Then, okay, so P gamma, it acts upon these vector spaces. It also acts upon all the tensor spaces we can make by tensoring together these guys and their duals. So we can make it act on the curvature. So we can say P gamma inverse of the curvature at the point x1 lies in the Holonomy group of the algebra of G, again tensored with the two forms on X. So this is what happens at our favourite point. At any other point, we can just take the curvature there, transport it back to x0 by parallel transport, and it will again lie in the same vector subspace of the place where the curvature tends to live. Okay, so hence the Holonomy group of G places at linear restrictions on the curvature of G. So actually this this whole thing is true generally for Holonomy groups of connections on vector bundles. There's nothing special about the Riemannian-Lebedev case, although in the general case you'd be wanting to say endomorphisms of the fibre of your vector bundle E at x0 rather than endomorphisms of the tangent space. Okay, so let's give you a sketch proof of this. Okay, so, well, let's take V and W be vector fields on big X. And let's suppose, for simplicity, that the Lie bracket is 0. So, for example, these could be the vector fields d by dxi, d by dxj, or coordinate derivatives in some coordinate directions for local coordinates on your manifold. And let's take epsilon greater than 0 be small. And let gamma be the parallelogram in X. So I want to start at my base point x0. I want to follow v for time epsilon. So we can think about that as x0 plus epsilon times v. So I follow the flow of v for time epsilon, and then I follow the flow of w, again for time epsilon. So this can be x0 plus epsilon v plus epsilon w. Then I follow the flow of minus v for time epsilon, and then I follow the flow of minus w for time epsilon. So that's x0 plus epsilon w. So got by starting at x0 and then following, flowing along V for time epsilon, and then W for time epsilon, and then minus V for time epsilon, and then minus W for time epsilon. Okay, now the fact that the vector fields V and W commute implies that when you go around this, when you do these four things, you get back to the same point. If they didn't commute, then you get back to some other point which would differ by order epsilon squared, and would have to somehow the direction between the two would have to do with the Lie bracket there. Okay. So the question is, so gamma is this piecewise smooth path, piecewise smooth parallelogram. My question is, what is the parallel transport around gamma, the small epsilon? So what is P gamma, the small epsilon? Well, you can do a kind of Stokes theorem, really. If you think about this as actually the boundary of a two-dimensional parallelogram, you can kind of do a form of integration around the boundary. So basically, because R measures whether the derivative in direction V using the Lebedev connection, and the derivative in direction W using the Lebedev connection, whether these commute, we can show that the parallel transport P gamma, well, it's the dominant term is the identity map on the tangent space of X, and then the leading term is epsilon squared times R at the point x0 contracted with V at x0 wedged W at x0, and then so there'll be some power series in epsilon. Leading term is that, and then the rest will be order of epsilon cubed, or possibly epsilon to the fourth, not sure which. Okay. So hence, we can take a limit. The limit, as epsilon goes to 0, of P gamma minus the identity map on Tx0 of x over epsilon squared. That's not going to contribute to the limit. So this is going to be equal to R at x0 dotted with V at x0 wedge W at x0. Okay. And this must lie in the tangent space at the identity to the holonomy group of G, which is the holonomy, the algebra of G. Okay, because, well, both of these guys are elements of the holonomy group of G by definition. The holonomy group of G is the set of these things. So we're really looking at a path in the holonomy group which converges to there. So if you take the tangent vector along the path is this. Okay, well, so I'm passing over the fact that I've moved from epsilon to epsilon squared, but that doesn't really matter. So you can think about this as this element here is a tangent vector to the holonomy group at the identity. Okay, so therefore, and you can choose any two vectors at the point can be extended locally to commuting vector fields. So therefore, R dotted with any 2 vector has to lie in the algebra, which basically proves this claim here. And you can get the claim for other points just by considering, instead of taking that to be x1 and having an x0 here, and considering a path which goes that way and then back again the same way. Okay, right, so this gives you kind of a connection between the Lie algebra of the Lonmy group and curvature in kind of one direction. There's actually a converse to this. So there is a converse to theorem 2.1, which is called the Ambrose-Singer holonomy theorem. Which I think is also true for general vector bundles and connections rather than merely Riemannian metrics and their Levi-Chivsky connections. This says that the holonomy Lie algebra, curly hole of G, this is the Lie subalgebra of the Lie algebra of endomorphisms of Tx0 of x, which is generated by anything we can make of this form after parallel transport from other points in the manifold. So generated by all elements P gamma inverse of curvature tensor R at x1 dotted with v vec w, and this is for all well, so gamma goes from 0, 1 into x, is a piecewise smooth path from x0 to x1, and v and w are any 2 vectors in the tangent space to x1 of x. Okay, does that make sense? So basically we can reconstruct the Lie algebra of the holonomy group out of the curvature in at least a certain sense. So for example, if the metric is flat, if the curvature is 0 everywhere, you can see immediately that the holonomy Lie algebra is 0. That means that the holonomy group itself doesn't have to be trivial, but it has to be dimension 0, so it's discrete. Basically the holonomy group of a flat metric has to be finite or countable. Okay, so so, at least morally, the curvature that determines the Lie algebra of the holonomy group, let's say curly hole of G of the holonomy group, big hole G. But in fact, curly hole G determines reduced Halonmi group, big hole 0 of G. This is the connected component of the Halonmi group containing the identity, and if X is simply connected, then the Halonmi group is connected, so hole 0 of G equals hole G. So in the case in which X is simply connected, then in some sense the curvature of the metric determines the entire Halonmi group. Okay. Right, so next let's actually go ahead and state Berger's theorem, which is gives you a classification of the possible Halonmi groups of Riemannian metrics. And this is definitely about Halonmi groups of Riemannian metrics. It's no longer to do with Halonmi groups of connections on arbitrary vector bundles. So let's have a new section 2.4 about Berger's theorem. So this was proved by Marcel Berger in 1955 as his PhD thesis, and I expect all of you guys doing PhDs will do something equally important. So if we let X and G be a Riemannian manifold, so let's have dimension n, so a Riemannian n manifold, then is a natural number. And we put in some simplifying assumptions. So we suppose that, firstly, that the manifold big X is simply connected. And that G is irreducible and non-symmetric. So I'll talk about these very shortly, and I'll also explain what happens if we were to leave these assumptions out. But let's just accept them for the moment. So the conclusion is that the Halonmi group of G is one of so there's going to be a list of 7 possibilities. Firstly, SON. So I'm going to leave a bit of space on the right-hand side to write some extra stuff. Secondly, U of M for little n is 2 times m. And, well, we can kind of, if we like, we can put in the restriction m is greater than 2. Thirdly, SU of m for n is 2m, and again, if we like, we can put in the restrictions m at least 2. Fourthly, SPM SP1. Now for n is 4 times m, and again m is at least 2. Actually, even here we can have n is at least 2. Fifthly, what have I done? Sorry. My fourth one is SPM. My fifth is SPM SP1 for n is 4m, and again m is at least 2. 6 is G2. Now only if n is 7, and 7th is spin 7 for n is 8. Okay, so I'm going to spend some time discussing this. So one thing to say is that all of these, they're not just, I'm giving the holonomy group not just as abstractly groups, but as particular subgroups of SON. Okay, or if you like, it's a group and a representation. So you're not allowed to choose an arbitrary embedding of G2 in SO7. You're choosing a particular, somehow the usual representation of G2 on SO7, or the usual embedding of UM in SO2M. Okay, so it's groups and representations I'm specifying. So secondly,
what if the X is not oriented?
If it's simply connected, then it's orientable. If it's not orientable, then you have to have a Z2 in the fundamental group somewhere. So the being simply connected excludes the non-orientable, which is when you'd get O of n, which I guess is what you're worrying about. Okay, so these conditions here are, perhaps I'll start on another board. Okay, so then the conditions m greater than 2 and so on, they're to avoid repeats. So you don't need them. It's just that if you leave them out, then some groups appear twice. So in particular, you have when n is, I suppose, n is 2, you have somehow SO2 is really an SO1 cross an SO1, morally speaking, because this is just trivial. So this is actually a product holonomy group. For when n is 4, you have SU2 is SP1 and SO4 is SP1 SP1. So the m equals 1 case. What have I done? Yeah. So the m equals 1 case here equals the m equals 2 case there. The m equals 1 case here equals the m equals 2 case, n equals 4 case here. Okay. So let's explain the restrictions on X, that is of being simply connected and irreducible and non-symmetric. So the conditions X simply connected and G irreducible and non-symmetric basically simplify the problem. So, well, without them, the list will be much longer. But nonetheless, Berger's done all the important work. But essentially still computable given Berger's theorem and other things we know. Okay, so, well, firstly, X simply connected implies whole of G is connected. Because if X is simply connected, then every loop in X can be contracted to a point. If you think about what that means, the parallel transports are along those loops. It means every point in the Holonomy group of G can be connected to the identity, which is the parallel transport around the constant path, by a path in whole G. So whole G is path connected. And well, so if we omit X simply connected, then, well, the reduced Holonomy group, whole 0 of G, still lies on Berger's list. Well, so we're going to call, okay, so this lot is going to be called Berger's list. Then whole G lies on Berger's list. And whole G will be the extension of whole 0 of G, well, let's say as whole 0 of G is the Holonomy group of the universal cover. We can take the universal cover, x twiddle of x, and we can lift the metric to a metric on the universal cover, and then that will be simply connected. And then whole G will be the extension of whole 0 of G by a finite or countable group. So you'd have to do some group theory to find out what the possibilities there are. Well, so we say that G is globally, well, let's say x comma G is globally reducible if it's a Riemannian product. Well, xg is isomorphic, is a Riemannian manifold to some product y cross z, well, h1 cross, well, let's say y1 cross y2, h1 cross h2. So a product of Riemannian manifolds of positive dimension. So for dimension of y1, dimension of y2 greater than 0. And as I told you at the beginning of the lecture, in this case, the holonomy group of H1 cross H2 is a product of the holonomy groups of H1 and the holonomy groups of H2. And therefore, the representation of the holonomy group of that is reducible. Okay, so...
sorry, when we say isomorphic, what's isomorphism in this?
Isometry. So the natural notion of isomorphism of Riemannian manifolds. So there's a diffeomorphism from there to there which identifies G with that. So we say x comma G is locally reducible if it can be covered by open neighborhoods which are globally reducible. So, okay, so even if something is globally reducible, if you take an open subset of it, which is not a product of open subsets, then the open subset won't be globally reducible anymore, but it will be locally reducible. And we say xg is irreducible if it is not locally reducible. Okay, so this buys us something. So if we're assuming the thing is not locally reducible, so if x and g is irreducible, then the representation of hol of g on R to the n is irreducible. Okay, so that's a slightly non-trivial fact. If you had a holonomy group, a metric with a holonomy group whose action on R to the n was reducible, so R to the n splits into the direct sum of two pieces, on each of which the holonomy group has a separate representation, you can use a kind of parallel transport to define a kind of, local foliation, the sort of local product structure on the entire manifold. And then in open sets, you'll find that these actually would turn in, these would force the metric to be locally reducible. Okay, so what this buys us is that we can assume that the holonomy group acts irreducibly on R to the n. Okay, so to allow G reducible, we'd need to include, or need also to include all, well, multiple products of groups on Berger's lists. Okay, so there's kind of no more work to do really in allowing things to be reducible. You know, you'd need to include things like U of 2 cross U of 3 acting on R to the 10, which is C to the 5, and so on. All multiple products of things in there would have to go on your list. All right. The third condition is of being non-symmetric, so let's define that. So, well, a Riemannian manifold X, comma G with Riemann curvature R is, well, locally symmetric if nabla of R is 0. So the Riemann curvature is constant under the Lev-Achieved connection. And it's and non-symmetric if it's not locally symmetric. So if nabla R is non-zero at least one point, then it's non-symmetric, and that's an assumption we make up here. So, there is a class of Riemannian manifolds called symmetric spaces. They're characterized by the fact that they have awfully large isometry groups, basically. At every point, there's a kind of reflection isometry which fixes that point and acts as -1 on the tangent space. So they are homogeneous spaces. G over H for H contained in G Lie groups. So examples would be things like projective spaces, spheres, hyperbolic spaces, there's some weird thing called the Cayley plane and so on. And they can be completely classified using Lie group theory. So there's a big book on them, I think, by Helgason or something. We're doing for time. Running out of time. So you can understand all symmetric spaces by what we know about Lie groups, and you can compute the holonomy groups of symmetric spaces as well. And a locally symmetric manifold, Riemannian manifold, is locally isometric to a symmetric space. So basically, if we're not non-symmetric, then open neighborhoods of our Riemannian manifold are isomorphic to small open neighborhoods of a symmetric space. So to drop the assumption that G is non-symmetric, you need to add the holonomy groups of all symmetric spaces. Well, so these are the known holonomy groups of symmetric spaces to our list. So, bother. If you don't mind, I want to add a few things to the right-hand side here before we stop. So, a comment here is that these are, for generic metrics, SON, basically, and SON is a boring Lonely group. So, if the Lonely group is SON, that says nothing interesting about the metric, really. U of M are what's called Kähler, and we'll be spending a lot of time talking about these. SUM are what's called Calabi-Yau. They're Ricci-flat Kähler metrics. SPM are what's called hyper-Kähler. SPM, SP1 are what's called quaternionic Kähler. Which is a slightly misleading name because, well, so the hyperkähler, and so these guys are all examples of Kähler things. Quaternionic Kähler things are not Kähler. And the last two things are what's called the exceptional Lonely groups. So there are lots of classification problems in geometry and other things, such as, well, classification of finite simple groups, classifications of Lie groups. You'll find that there are some, you tend to get some number of repeating families, and then in addition to the repeating families, which I'll mention or whatever, you also get some finite number of exceptional cases in your collection. So in this case we have 5 repeating families, which depend upon some natural number, and then we have 2 extra ones, and these are the exceptional cases in our classification. All right, let's